this video we're going to go back and revisit maps. So we now have this really good understanding of both a tree, binary search tree in particular, as well as a hash table. So now we're going to talk about how these data structures help implement our map. So in C++, the map container is a key value map, abstraction that allows you to take a key and quickly look up and efficiently look up a value using a binary search tree under the hood. And the binary search tree kind of takes a little bit to kind of think about how the binary search tree is actually used to implement the map. And so the way that it works is that your keys are used to actually sort out the tree. So you have to choose some value to decide whether to place a node to the left or the right of each other node, right? And so with a map, since the key is the value that you use to do lookup, the key is the item that's actually used to build a tree. Then for maps, because you do have key value pairs that you're storing together, inside of each node the value is stored alongside it. So that means that the key will get you to the node, and then once you're there you can access the value. A tree could store anything that you'd like in that node, but for the map abstraction, the way that it works is it only needs to keep track of those two things. So as we know, if you are looking up something in a map using a tree, you basically navigate down the tree, so you walk the height of the tree, and that is a log n complexity for insert, remove, and search. So that's how the map abstraction works and the map container works in C++. And generally, if you use the term map, it doesn't necessarily imply how it's implemented. So when you generally outside of C++ refer to a map, you shouldn't assume that it's necessarily implemented with a tree or a binary search tree or anything else. So a map is a general term for a key value pair. In C++, the hash map abstraction is called an unordered map, but it's not really called that, outside of C++. And so hash map is the more general term for a map that's specifically implemented with a hash table. So map is general. It doesn't really assume any implementation, but hash map is a specific type of map. So if you're ever talking about maps and hash maps, particularly if you're ever talking about them like in an industry setting or in an interview or something, just know that depending on the background language of the person you're talking about, some of the C++ terminology might not be the same. So in C++, the unordered map is also a abstraction that's able to keep key value pairs, store key value pairs, but the way that it does it is it uses a hash function. So when you send a key into the hash function, it gives out an index, and that index is used to directly access a particular element in a table, which is just an array, nothing fancy. And once you get to the spot in the array where the hash function points you to, then basically all the data would be stored there. So in this case, for a map, it would just be the value. And you don't need to store the key with the value typically, because you already have the key when you looked it up, and you just need the hash function. So that's not true. Sometimes you do need to store the key, particularly if you have collisions. So it would just depend on how it was designed. Probably in most cases you would actually need to store the key. Okay. So these are the two types of maps that we've learned about, and now we also are able to understand how they're actually implemented. So they're designed to be interchangeable, because they both do the same thing. So the way that the container is actually implemented in C++ is that you'll see that it looks exactly the same. In fact, if you write out code with a map and you want to change it to an unordered map, all you have to do is change the type. All of the functionality stays exactly the same. It's just how it's implemented behind the scenes. So let's say that we wanted to create a map that mapped net IDs to favorite food. And so both of those, the key and the value, are both going to be strings. And so we're going to do it first with the map. So that means it's going to be a binary search tree. So we'll just use the word tree just to distinguish the two. So we're going to first insert a couple of key value pairs into our map. So first we'll insert Professor Hummel's favorite food. His net ID is jhummel2, and his favorite food is pad thai. Then we're going to insert my favorite food, which is a vermicelli bowl, bun bo cha. And my net ID is just Shannon. It's just my first name. So that's how you insert into, and by the way, if you've never had a vermicelli bowl, it's amazing. It's like a vermicelli salad, I guess is the way to think about it. It's so yummy. Back to maps. So the square bracket, in C++ can be used to insert or to look up. It has some unusual behavior though, so you have to be really careful if you remember back to when we used it in the past. It has particularly unusual behavior if you're trying to look up something that doesn't exist in the map. It just goes ahead and adds it, so that's oftentimes not what you want. So there's other functions that you can use for insert and lookup as well. If you want to use the square brackets, you just have to be really careful. So that's how we fill the map, is just by putting stuff in with the square brackets and the equals operator. And then if we sorry, not like that equals operator that you override, just the equal sign to put it in. If you want to look up, let's say that we just took the lookup from the keyboard, you could just use the square brackets again, right, to look up. And otherwise you can use count, you can use find, you can use in place. There's all sorts of functions that you can use for both of these things. On the other hand, an unordered map, if we wanted to do the same thing, has the hash table under the hood, but using it looks exactly the same. So the only difference is we have a different variable here because we've set it up with a different variable, and then we have different types here. But otherwise you'll see everything else is exactly the same. And that's how C++ particularly is it has a lot of consistency across containers. Okay, so now let's just do a little bit of a demo and look at what this looks like in a couple different cases. So here's an example where we have inserted into 3 different types of maps. The first one here is the regular map, and then we have 2 different unordered maps with 2 different hash table or 2 different hash functions. And so a couple things that are interesting about this, we have outputted all 3 of the maps, and you'll notice that the ordering is different. So in the first example with the tree, you'll notice that it's ordered by key, the ordering of the keys. So F. Zizza, J. Hummel, and Shannon are in alphabetical order. And that's because we know that the binary search tree is sorting all of the data in order by key, and so when you loop through the abstraction, you are going to traverse the tree in order, and so you naturally get out the key value pairs in this order. When you look at the unordered map using a hash table, you'll notice that it's in random order. This is often the case because a lot of times hash functions have some randomness to them. They can. Now they don't have randomness, each time you put in the key it returns the value, but there could be randomness in the hash function itself, and typically you are doing enough to it that you can't kind of predict what the number is. And you kind of saw that with the string, I forget what it's called, the one in Zybooks, the string manipulation. I don't think I'm thinking of that right. I forget what it's called. That one is, it has so many different bit operations that you kind of couldn't no longer like mathematically predict what it would do as a human, right? Because it's like doing so much with the numbers. Okay, and then you'll notice that the hash 2 is in reverse order. So we inserted Professor Hummel, then me, and then F. Ziza in that order, and then you'll notice that it's printed in reverse insertion order. So the question is, well, why are we seeing this? Why is hash table 2 in reverse order and it doesn't appear to be in random order? And obviously this is a small number of insertions, but you would see the same thing even with a large number of insertions. So the reason is because this is the hash function. So a really terrible hash function that always returns 123, and you can see that down here as well. And so when you're inserting into the hash table, all of the keys are getting placed in the same spot of the hash table. So let's call that the index 123. And this particular unordered map that's being used here is handling collisions with chaining, so with a linked list. And so all of the items are getting inserted into the linked list, and they're getting inserted at the head of the linked list because that saves on memory, because you just have to move the head pointer in the hash table, and that's all you have to do. And so that's why it's in reverse order, because you're inserting to the front. And so then when you walk back through, you're going to get to the last one first. The last one inserted will be the first one printed. So a lot of this stuff is now stuff that you can really deeply understand. So when you're using these abstractions, probably in the past, you're just like, oh, why? That's odd. Why is it in that order? Or why does it do that? And now after taking this class and writing your own abstractions and implementing abstractions with specific data structures, you can start to really understand these things enough to be able to change them if you don't like how they are and implement your own, or be able to work within what is already there to make the best decisions for the problems that you're solving. So that's all I wanted to go over and look at again with maps. And keep it in mind, because we're going to continue to use them in the next couple of projects that we have. Thanks.